Hello, welcome to this particular lecture on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have been talking about the unknown quantities. So far, we have discussed that for n original buses, total number of unknown is 6n, 3n voltage magnitudes and 3n voltage angle. And for m internal buses, total number of unknown is 2m. As for every internal bus, only VIA and theta IA are the only unknown quantities, right? And for every internal bus, I would be varying from n plus 1 to n plus m. So, out of these 2m quantities, m would be m number of unknown quantities would be corresponding to the internal bus, would be actually corresponding to the voltage magnitudes, and the remaining m number of unknown quantities would be corresponding to voltage angles of the internal buses. So, here it appears that the total number of unknown is 6n plus 2m. However, we must note that we are also trying to calculate the angles, and for calculating the angles we have to take one reference angle which we have to assign a value to be 0. So, then therefore, out of these total number of angles, so now here total number of angles, so then therefore, out of this, so here total number of unknown voltage quantities is actually 3n plus m. 3n are for this original buses and m is for internal buses. And it also appears that total number of unknown angles, unknown voltage, I should say unknown voltage, language wrong. Unknown voltage magnitudes is 3n plus m, and total number of unknown voltage angles appears to be 3n plus m, but we must understand that for calculating the angles we also need to take one reference angle, and that reference angle will have to be among these unknown quantities. So, then therefore, we will take one reference angle. So, as a result, that particular reference angle would be given a value of 0, or rather would be actually pre-assigned a value of 0, as an example, as we do in the same way in the case of single phase load flow analysis. In the case of single phase load flow analysis, we do assign the voltage angle equal to 0 for the slack bus. So, here also we have to take the voltage angle of any particular angle to be 0. So, then therefore, we do not have to estimate that, or rather we do not have to really calculate that. So, then therefore, my total number of voltage angles would be 3n plus m minus 1, right. So, therefore, total number of unknowns is now is 6n plus 2m minus 1, right. So, then therefore, in our case for n is equal to 5 and m is equal to 3, my total number of unknowns is 6 into 5 plus 2 into 3 minus 1, that is 30 plus 6 minus 1, 35. So, for a simple 5 bus system, the unknowns is 35. Now, what are these unknowns? So this 6n plus 2m minus 1 unknowns we do classify into 4 categories. So we now look at classification of unknown quantities. So what are these unknown quantities classification? So A is voltage magnitudes at all original buses corresponding to all 3 phases, right. So this is first. So the total number is, so then therefore this we denote as a vector v, and this vector is say v1a, v1b, v1c, v2a, and then so on and so forth, dot dot dot, let us say vna, vnb, vnc, right. So there are total n number of buses. I can also, just for the sake of clarification or clarity, I can add some more v2a, v2b, v2c, and then dot 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 up to vna, vnb, vnc transpose. So for every bus the unknown quantities are v1a, v1b, v1c, v2a, v2b, v2c, and then dot 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 up to this vna, vnb, vnc. So this is total is 3n cross 1. So total number of unknown is 3n cross 1. Then now we said that we have to take one angle to be the reference angle. Usually what we do is that we take the phase A angle, phase A of the bus 1, or rather we should say that basically we do take the angle of phase A of bus 1, we do take as the reference angle. Let us say convention, let us say let theta 1a be taken as the reference angle, right. So that means theta 1a is equal to 0. That means the unknown angle, unknown voltage angles for all original buses are, they are taken in a vector theta, and that vector theta would be theta 1b, because theta 1a I do not need to solve because theta 1a is taken as the reference angle, theta 1b, theta 1c, then theta 2a, theta 2b, theta 2c, then dot 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 theta n A, theta n B, theta n C. That would be transpose. So this will have 3n but minus 1. So then it's 3n minus 1 cross 1. So this is a vector. So then this particular theta vector is 3n minus 1 cross 1. Third classification is voltage magnitudes at the internal buses. Right. So these we denote as a vector V internal, and we denote it as V n plus 1 A, V n plus 2 A, V n plus 3 A dot 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 V n plus m A. So that is the internal buses. So for all internal buses n plus 1, n plus 2, n plus 3 up to n plus m, the internal buses, the voltage magnitudes are unknown. So this is transpose T. So this has got total m cross 1. And then voltage angles at the internal buses. So that we denote as theta internal vector, that is theta n plus 1 A, theta n plus 2 A, theta n plus 3 A dot 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 theta plus m A transpose m cross 1. So then therefore my unknown quantities are now basically represented into 4 sub vectors. So my unknown quantities are now 4 sub vectors: v, theta, v int, theta int. V has got a dimension 3n cross 1, theta has got a dimension 3n minus 1 cross 1, v internal has got a dimension m cross 1, theta internal has got a dimension m cross 1. So altogether I have got total number of unknowns 6n plus 2m minus 1. So obviously to do this, now obviously to solve for this we also need 6n plus 1, 6n plus 2m minus 1 number of equations. So we must write it very boldly to solve these 6n plus 2m minus 1 unknown quantities. We need 6n plus 2m minus 1 equations. Right. At a later stage we will give one example for these different variables by taking a very small system, so that these ideas are made more clear. But right now let us go into the equations. What would be the equations? Now before we do the equations, before we talk about the equations, we need to understand first the power flow equations. Now, what would be the power flow equations? Now, here we one important observation, one important observation is that one important observation is that the Y bus matrix needs to be essentially the Y bus matrix after the augmentation. One important is that the Y bus matrix needs to be formed by taking into account the internal buses also. So, this is very important. You see, originally when we have talked about the Y bus matrix, we said for an n bus system, the size of the Y bus matrix is 3n cross 3n, right? Y11, Y12, Y1n, and etc. 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 Correct. So, then therefore, for an n bus system, for original n bus system, the size is 3n cross 3n, size of Y bus matrix. Matrix is 3n cross 3. But for augmented system, but please note we have to now, for example, here we said that my original system which we have considered is this. So, I mean this is my original system, bus 1, I think bus 2, bus 3, then bus 4, bus 5. So, for this system when we form the Y bus matrix, this is basically 15 cross 15. But then after we augment the system by the internal buses like this, so this is bus 6, this is bus 7, and this is bus 8, this is bus 8. So, then therefore, now my system size is actually 8 bus. So, now my augmented bus size is 8 bus system. So, for this system, so earlier my system was, so my original system was this. So, I mean this was my original system. So, this was my original system. So, this original system has got a size of 15 cross 15 Y bus matrix. But because now I have added 3 more internal buses along with their corresponding impedance matrices, my augmented system is now this. So, now my augmented system is basically comprising of all 8 buses. So, then therefore, the size of this Y bus matrix is 24 cross 24 Y bus matrix. So, we have to form the Y bus matrix for an 8 bus system, right, not for the original 5 bus system. So, for augmented So I should say that for augmented n plus m bus system, because now my system size has enhanced from n to n plus m. So augmented n bus system, the size of the y bus matrices is essentially 3n plus m cross 3 plus m, right? So this is very important observation. So we need to understand that the moment we do augment this system, so then therefore my total system size increases from n to n plus m. So then therefore I also have to find out the y bus matrix for the augmented systems, and so as a result its size would be 3 into n plus m cross 3 into n plus m. So now let us look at the equations. So what are the equations? Now equations means the known quantities. So now equations, so once, I mean we will talk about the equations essentially later on. So rather equations, and these equations would be, we should actually write it, equations or essentially known quantities, because after all these known quantities will give us the equation. So let us first talk about the known quantities, not the equations. Equations we will talk in at a later class. So let us talk about the known quantities. How many known quantities? I need to have 6n plus 2m minus 1 known quantities, otherwise I cannot solve. So now what are the known quantities we know? Again, to understand that, first let us look at this system original. So I have got original system 1 2 3 4 5, bus 3, bus 1 2 3 has been the generator buses, and bus 4 and 5 are the load buses. So let us say that bus 4 and 5 are the load buses. So at bus 4 and 5 I know all the 6 load quantities, right. So basically, as an example, at bus 4 I know what is P4A, P4B, P4C, or rather PL4A, PL4B, PL4C. Similarly, I know QL4A, QL4B, QL4C, right. Similarly, also at bus 5 I know what is PL5A, PL5B, PL5C, as well as QL5A, QL5B, QL5C. Now even if there is no load connected at bus 1 now please note, when we are doing this augmented matrix, we are essentially shifting the generator at bus 6 and bus 7 at bus 8. So then therefore as far as bus 1 is concerned, so then therefore there is no load connected. Now even if there is some load connected, so I know that what are the load quantities there. Even if there is no load connected there, I know still that what are the load quantities there, which is 0. So then therefore for each and every bus, if there is any load connected, so then therefore the injected current would be at that particular bus would be nothing but the negative of the load power. And even if there is no load connected at any particular bus, the injected power at that particular bus is 0. So then therefore effectively for each and every original buses, I know what are the injected real and reactive power. For example, in this case for bus 4 and 5 there are loads connected. So then therefore for bus 4 and 5, for every phase I know what are the injected real and reactive power. And for bus 1, 2 and 3 originally there were basically generators connected, but now we have actually shifted the generator from bus 1, 2, 3 to bus 6, 7, 8 respectively, that is we have shifted the generators to the internal buses. So then therefore at bus 1 there is no generator connected. Now if there had been any load connected at bus 1, 2, 3 earlier, so then therefore in that case the injected power would have been the negative of this load powers. But here let us assume that at bus 1, 2, 3 there had been no load connected, so then therefore injected power um, at these 3 buses, bus 1, 2, 3 are all 0. So then therefore I know that for every original bus, so I can say that for every original n buses, we know that Pi A, Pi B, Pi C, Qi A, Qi B, Qi C are known. Now, what is PIP and QIC? Where PIP or QIP is nothing but real or reactive, within bracket reactive, injected power at bus I corresponding to phase P. So I is so that means total number of known quantities is here 6n. What do I know? For every generator, we should know the injected power, or rather what is their power generation. However, as we know from our knowledge from the load flow analysis, we cannot pre-specify power for each and every generator. At least one generator power we have to keep free to take into account the losses which we would be able to compute after the load flow analysis. So then therefore, out of m generators, we would be able to pre-specify the generated power for the remaining m minus 1 generators. So then therefore, we would be knowing that generated power by m minus 1 generators. So for generated power by each of the m minus 1 generators, one generator we will keep as a slack, for which we would be calculating the power after the load flow is computed. So generated power by each of the m minus 1 generator, which we can actually pre-specify. So then therefore total number of known quantities is m minus 1. What else we know? We also have to pre-specify the voltages at for every generator. Please note, even in the case of a single phase load flow analysis, even for the slack bus, we do actually pre-specify the voltages for every generator. So for Here also, in this case also, even for the slack bus, we would be able to pre-specify the voltages for every generator. So, the pre-specified voltage for every generator so therefore total number of known quantities is right. So, the grand total is 6n plus m minus 1 plus m, that is 6n plus 2m minus 1, which is equal to the number of unknown quantities. So, we have managed to get exactly the same number of known quantities, that is equal to 6n plus 2m minus 1 known quantities, and we have got exactly 6n plus 2m minus 1 unknown quantities. So, then therefore, we should be able to solve. So, from the next lecture onwards, we will start talking about the equations for these known quantities, right. So, that these known quantities are actually expressed in terms of the unknown quantities, and then after that we will look into the method, at least one method, that is basically the Newton-Raphson method for solving those equations. Thank you so much.